So here we have this information we got out of the question about the aluminum. And then what's going on here? There's a drop of water, right? A drop of water condenses. So here's, ooh, that was a big drop of water. I didn't want it to be that big. Let's see. So here's a drop of water. Drop of water condenses on the aluminum. What do we know about the drop of water? We know that it's 0.48 grams. And what temperature is the water, do you think? Probably the same as the aluminum, right? Doesn't matter a great deal, but just kind of thinking about that. So now what's going on here? So this is telling us that water condensed onto the aluminum. Is that going to absorb heat or give off heat? That's hard to think about, isn't it? Condensing. Let's think about the opposite. What's the opposite of condensing? Evaporating, right? To get something to evaporate, do you put heat into it or take heat out of it? We put it in, right? So if we put heat in to make something evaporate, then when it condenses, the heat must come back out. So this water droplet is giving off energy. Could we figure out how much energy it's giving off? Yes. Yes, we could. We've got 0.48 grams of water. This is very much like the problem we just did, except instead of vaporizing it, it's condensing. There was a number in a table. They're not giving it to us in the problem. This is most likely occurring at 25 degrees Celsius. The heat of vaporization for water at 25 degrees Celsius is 44 kilojoules per mole. It was in the table. I just happened to remember it because I did it this morning. So if we know the mass, let's just point over here. If I know the mass of the water, I could convert that to what? So that I could get to kilojoules, moles. Because the heat of vaporization gives me the amount of energy to do something to 1 mole. So I need to convert to moles. Well, we already figured out what the molar mass of water was. It was 18.02. We're going to double check our units here that they cancel out. So this is the same calculation we did, just with different numbers. 0.48 divided by 18.02 times 44. So that's 1.17 kilojoules. And that is heat lost by the water. Sometimes it's helpful to kind of label things. Here in the problem it says if the heat released during condensation goes only toward heating the metal. Now that's not true, that wouldn't happen, but we're told to assume that to make things easier. So we're going to assume that all of the heat from the water condensing is going into the metal. And they're asking us what the final temperature is. Does that sound vaguely familiar? Yeah, we did stuff like that before, didn't we? With delta T's and C's and things. We had this little equation, and we did some stuff in lab with styrofoam cups. Do you remember that? Q equals MC delta T. Where Q was the amount of heat, M is the mass, C was the specific heat capacity, and delta T was T final minus T initial, was the change in temperature. Well, do we know any of those things? Yeah, we do. Let's go up here and label them. So 0.903, that's the specific heat capacity, that's C. 55 grams is the mass. And 25 degrees is the initial temperature. The problem is asking us, what's the final temperature? Well, if we know the initial temperature and we calculate the difference, then we could figure out what the final temperature is, right? So let's take this equation, and we want to find the change in temperature. So I'm going to rearrange this. I'm going to divide by MC to make those go away. And then over here, I'm going to divide by MC. And so now I have an equation that says the change in temperature is equal to Q divided by the mass times the specific heat capacity. What's Q? So we got this equation, but what's Q? That's this guy over here, isn't it? The water droplet gave off heat. That heat went into the block of aluminum. That's our Q. That's the heat. So we'll stick that in here. 1.17 kilojoules. And the mass up there on the top, 55 grams. And the specific heat it gave us 0.903. And the units on that are joules per gram degrees Celsius. Let's look at those units. Are they going to work out okay? No. Grams are fine. Those are going to cancel, but kilojoules and joules don't cancel. Well, we need to convert, right? We need to convert kilojoules to joules. So what if we take off kilojoule and write what kilo stands for? Kilo stands for 10 to the third. And then we'll put the J back. Does it seem magical? It's not magical. All I did was I took K, and instead of writing K, the abbreviation, I wrote 10 to the 3, which is what it means. So now we have something we can do something with. So the joules cancel out, and those degrees Celsius will come up where they're supposed to be. 1.17 EE3 divided by 55 divided by 0.903 equals we got 2 sig figs on the mass, and our temperature up there is only 2, so we're going to round this off to 24 degrees Celsius. Is that the answer to the problem? Is that the final temperature? No. Because you know, if you have a brain fart and think, oh yeah, that's the final temperature, ask yourself, does this make sense? The water gave energy to the block of wood, the temperature should go up, right? And the temperature went down to 24. Oh no, that was the change in temperature. So this change, are we going to add that to 25 or subtract it? We're going to add. So we're going to take our 24 plus 25, and we're going to get 49 degrees Celsius. Any questions?